So we're going to start with number 6. Remember, if you're not working on it, this one, you work on it, that's fine. Just try to keep it down a little bit so that I can hear. What is the ideal banking angle for general turn of this on a highway of this with this speed limit? Now remember, the ideal banking angle would be the speed that you took, the design speed matching the speed limit. In other words, you could take this corner without needing any additional force, like from friction. If you take it too slow, you're going to need friction so you don't slide down the slope. If you take it too fast, you're going to need friction so you don't go up the slope. But at the ideal speed for this angle, for this curve, no friction is needed. You can take it on ice and still make it around. So that's kind of part of what you would need a force diagram in here, so we'll draw one. But you would put things like going in circle, therefore need acceleration towards center. And the force to create this acceleration also points towards center. Up circle. In case that wasn't. And the real, I think, for me, the essential part of when I do this one is making sure that I get the understanding in my diagram. So I'm going to draw a diagram. If I was looking at it end on and the car was coming at me, so I'm going to draw, there's the bank, and here's my car going around the bank. And the car is coming at me, so let's see, we'll give it a radiator grill, and a windshield, and an antenna. And it's coming at me, so its velocity is coming out of the board. Here's the angle theta. And because we're at the exact design angle, remember I don't need any friction, so this car isn't trying to slide up or slide down the bank. It's going to have a force of gravity downwards, and it's going to have a normal force in that direction perpendicular to the plane. And so, therefore, it's going to be accelerating in this direction centripetally towards the center of the curve. And it's actually going to be a component of that normal force, which is going to be what provides the force to give it this acceleration. So, I'm going to draw a little free body diagram below this just to help me out in my rationale. S of G down here, force normal up here, my acceleration. This diagram wouldn't be needed, but I like it is in that direction. So I'm going to take the components here of my normal force, which would be these two, and let's see, trying to think, this is that angle, then this, I think this angle should be theta. Right? Sorry, just Friday getting my head around. Yes, that angle. That angle up there is theta. So the horizontal component here of the normal force is actually what is providing the centripetal acceleration and so we'll call this force normal perpendicular, and this side, the force normal, we'll call it force normal parallel, is actually going to balance the gravity. So, where I'm going to start off now mathematically is that with the sum of the forces is MA, our good old Newton's second law. And let's change those from parallel and perpendicular to, we'll call this one X, and this one in the Y direction. So, I'm going to go sum of the forces in the Y equals MAY. Sum of the forces in the X equals MAX. In the Y, I've got two forces. Force normal Y. Whoops. Horrible end. Force normal in the Y direction minus F sub G equals 0. So force normal in the Y would be the same as the weight of the car. Yes. Flooding back from months ago. In the X direction, I'm going to switch to green. The only force I have in the X direction is F, force normal in the X direction. That's going to equal M times the acceleration centripetal, which is in that direction also. So, okay, lots of fun, but what do they want to know? They want to know what's the angle, right? The ideal banking angle. All right, so you can substitute in here force normal X equals M V squared over R, because we have the centripetal acceleration, which is V squared over R from our equation sheet. And we also know force normal Y here, this would be M times little g. That's our definition of weight. So if I look at my triangle over here, I can either do Pythagoras, or I'm going to use the trig, so that the tan of theta equals opposite force normal X over adjacent force normal Y, and substitute in what I know here. Force normal X is M V squared over R, and my force, whoops. Okay, sorry, I did that right. M V squared over R, and my force normal Y is mg. And so, oh, my m's cancel out nicely, right? I know my v, because they tell it to me. It is 105 kilometers an hour. Now, we could leave it in kilometers an hour, right? The only problem would be, let's think if we could leave it in kilometers and kilometers an hour, just to see if we could save ourselves some. V and R could both be in kilometers, right? In kilometers an hour. The problem is G. We need to convert G to kilometers per second squared. That could be more of a pain than converting the other ones. So I would convert your velocity to meters per second and your radius to meters, so you can use 9.80 meters per second squared for G. Remember, you can use I can show you how to use side tools in your calculator. Remember how to do that? Yeah, you want your velocity, like mine right now is in kilometers per hour, right? What is it? 105. I have 105 kilometers per hour. I want to get that into something in meters per second. And my radius, 101.75, is 1.75 kilometers. I want to get that in something in meters, well, 1,750, right? And then I'll use my G as 9.80 meters per second squared. Well, then my next mathematical step here would be to say, okay, I want theta, that's going to equal the inverse or arctan of, and I'm just going to simplify this to v squared over r times g. It's v squared over r over g, which, if I think about that, it's v squared over r times 1 over g. And then that should lead us to the correct answer. So if you need help with the individual math, let me know. I will double check because it is Friday. All right, so number one been requested. We'll see if we can do this real quick. This is one that actually wouldn't need a force diagram because it's all about accelerations. And there's a common mistake that actually a diagram clears up on this one. But your Y would focus in, you guys remember? Your Y should focus in on the fact that the space shuttle is moving in a circle, and we're given here the period. Now, so your Y would have, this is number one, you would have in circle, blah, 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 blah. But I think what's crucial is to do a diagram in here because I think it makes it very clear. Here's our happy little satellite, and it's going in this circle like this, and the Earth is here in the center, and they tell us that this distance here is 440 kilometers from me, and they want to know the centripetal acceleration. We're going to use AC is 4 pi squared r over the period squared. R, remember, is the radius of the circle. Well, the radius of the circle goes from the satellite to the center of the Earth. So for the radius of the circle, for me, it's going to be 440 kilometers plus the radius of the Earth. Because they gave me from there to the surface. This is one reason I put this in here is remembering this fact that it's from center of the Earth that is going to, will be very important next week when we're doing gravity. If I go with my equation sheet here, there's a whole list of, radius of the Earth and moon and all sorts of things like that. So the radius of the Earth is 6.38 times 10 to the 6th meters. So my radius is going to be 440,000 meters plus 6.38 times 10 to the 6 meters. So that's my radius. My period, the time for one rotation, is told to me 93.4 minutes, but I would want that in seconds. So I would convert my period that I'm given to seconds, and then be able to put that in. And they want it in terms of G, So when I'm all done, I'm going to take whatever answer I get for A sub C in meters per second squared, and I'll divide that by G, 9.80 meters per second squared, and get my acceleration in terms of little g. I went to my equation sheet, and I noticed that R, Earth, is 6.38 times 10 to the 6 meters. R stands for radius. Earth is what radius you're describing. All right, I gotta see.